Greetings and welcome to week 4, unit 2. What is engineering? In the earlier unit, we described some features of 4 general categories of knowledge. And we also said that there, there, there can be additional categories of knowledge specific to engineering discipline. Now, we want to explore what these are. But before we do that, we need to understand what engineering. Unfortunately, there are a lot of prevalent implicit or explicit view that not only by people who work in the area of science, but professors who work in engineering departments also, they hold the view that engineering is nothing but applied science. Some of these statements are written by very, very senior top professors in their textbooks as well. It is, in my opinion, one of the most unfortunate things to happen for engineering. They might have contributed a great deal for engineering, but in general, if you consider that engineering is nothing but applied science, you are doing a great disservice to engineering. And people around the world are trying to correct this misnomer or this wrong idea that engineering is a kind of a subset of science. It has grown over several decades, but now it will take a lot of time for it to get back to a stage where engineering is something. Its goals and methods are different from that of science. Unless you acknowledge that, you will not be able to train your students as good engineers. Okay. Teachers in engineering programs should consider the courses they teach as elements of a program in which all students need to attain well stated outcomes at the time of graduation. That is the first thing that all teachers should acknowledge to themselves, that if I am teaching 2 courses in electronics, one course in something like applied mathematics course, that is not completely engineering. Because when I am giving this, whatever knowledge that I am trying to want my students to acquire, it's part of their overall training. That is what you have to realize. That means any decision that you take about your own course should be within a bigger context rather than within the context of that particular subject itself. Okay. And teachers need to facilitate their students to become good engineers. When somebody enters an 4-year engineering program, what is the purpose? The purpose is to become good engineers. That's it. So we need to know who defines who are good engineers. Unfortunately, the NBA defined the program outcomes of engineering programs characterizing good engineers. If all students attain these outcomes at the time of graduation, then they are good engineers. We are characterizing like that. But majority of engineering programs in India, though the program outcomes have been written or been published about 10 years back, still majority of engineering programs in India do not yet measure up to meet the program outcomes. If you seriously look at whatever be the institution, they do not really measure up to the fact that they have great faculty, great resources, good students doesn't mean that they are good engineering programs. or they meet these program outcomes completely. So, because if somebody said you have to meet these program outcomes, and I look at that sentence and say yes, as we have already explained earlier in earlier units, and I tick a box. When I tick the box, I consider that I achieved. Okay. So, to truly internalize the importance of these program outcomes, uh, the, all concerned people should become aware of what engineering is, or whatever controversies that exist, so that you can take a particular position about it. What is engineering? Many persons concerned with engineering education consider that engineering is applied science, or there is no difference between science and engineering. I've in my interactions with fellow professors at even top institutions, there any time that this particular issue is raised, they say, "Why do you want to raise any difference between science and engineering? They are the same. Then why not use only one word?" But that you are not willing to use. Why not call everything engineering and science is a part of it? Or why not call everything as science and engineering a part of it? We still use that. That means these two have some relationship. That relationship, majority consider that engineering is applied science. When you add an adjective to something, that means it is a subset of the something, right? So the model for that would be, if engineering is applied science, then studying the epistemology of science should automatically subsume the knowledge content of engineering. That is, if I know all the underlying science, then I know engineering. It is only I am applying with respect to one particular issue. So the model is, the science is a circle, applied science is a, whether you want to make this big or small, that is your view. It's a subset of science. Now let us look at how formal bodies define engineering. EBIT, actually our National Board of Accreditation has been following, or has been, because they have been guided by EBIT in planning their accreditation process. And to that extent, they directly borrow the EBIT, not directly borrow, they write the program outcomes in that spirit. The actual program outcomes come from Washington Accord. EBIT doesn't use the same set of statements of Washington Accord for their outcomes. I wish NBA has used the same set of outcome or something similar to that of EBIT, but they use a much bigger, rather more complex statements as given by Washington Accord. Okay, here EBIT defines engineering. Engineering is a profession in which knowledge of mathematical and natural sciences is applied with judgment to develop ways to utilize materials and forces of nature for the benefit of mankind. This is precisely, you can say, that is, I restrict the activity, scientific activity, if I restrict in some way, it becomes engineering. So the key features of EBIT definition: application of science and maths, professional ethics and judgment, these are the additional things, and human and societal benefit. These are the additional thing. But the primary thing in EBIT definition is still, it is engineering is a profession in which knowledge of mathematical and natural sciences is applied to solve a problem under some conditions. Then there is another body, National Academy of Engineering, NAE USA. Engineering is a creative application of science and mathematics to design solutions for real world problems. So real world problems come, but still it is only a creative application of science and mathematics. The key features of this is application of sciences and mathematics, creativity, design solutions, real world problems. So one implication is, yes, I am solving a real world problem and all the required science and mathematical knowledge is already available. I just need to use the existing body of knowledge to solve my problem. If that knowledge doesn't exist, let's say required knowledge doesn't exist with me in whatever form, that the four categories that we talked about, conceptual, procedural and factual, if that is not available, then I cannot solve my problem on hand. I don't think we take that kind of position. If the knowledge is not available, still we are required to solve the problem. So we have to do something else. And that is unfortunately not reflected in these two professional bodies in their definitions of engineering. But incidentally, they do have a very dominant a role in the field of engineering education. So what are the implications of these definitions? The science and mathematics knowledge to solve real world problems is available. Who can guarantee that? The goals of engineering are a subset of goals of science. That means, do I have to keep on waiting until the required science knowledge from science and mathematics is made available? If it is not available, then I cannot solve my problem. The methods by which science and mathematics knowledge is produced are the same for producing engineering knowledge. These are the implicit assumptions of these two definitions. Let us look at history of engineering activities. Engineering activities are prehistoric, right from people who made, somebody made a tool, let us say using stone. That is an engineering activity, is producing a product or is making a device. Does he have to know the nature of the rocks, where it came from and what is to be done? His job is only will do by trial and error. And if he finds one particular procedure to give him a sharp object, that's it, he will follow. So engineering activity is as practically as old as humans, you can say. So let us take some specific things. Arch and dome structures. They have been there from Roman times. Implied structural mechanics and compressive force distribution was discovered 1500 years later, after the arch and dome structures started getting built. Okay, the concerned science came 1500 years later. Water wheels and irrigation systems, ancient China and Mesopotamia. Principles of fluid dynamics and energy conversion were discovered 2000 years later. Windmills, Persia in 9th century. Pressure differentials and aerodynamics were discovered 800 years later. Glassmaking, ancient Egypt and Mesopotamia. Thermochemistry and kinetic gas laws were discovered 500 years later. I don't think it is much more. Iron smelting and steel making, India 400 BC, the iron pillar in Delhi. Metallurgy, phase diagrams, oxidation reduction reactions were discovered 1000 years later, after that iron pillar was built. Now coming to a little modern times, steam engines was built by Newcomen 1712. Thermodynamics first law was was proposed by Clausius in 1840, 100 years after the steam engine was built. Sailing ships and navigation tool, Phoenicians, Polynesians, etc., fluid mechanics, celestial mechanics, uh, they came 1,000+ years later after the sailing ships were built. Scientific aerodynamics grew rapidly after the airplane was demonstrated to work by Wright brothers in 1900. Really speaking, aerodynamics was a formal discipline came into being around the Second World War time. Vacuum pump was invented in 1850, very much before science of pressure and air was established. Jet engine was created in 30s and 40s. Jet propulsion systems were developed and refined before full understanding of high-speed thermofluids and turbulence happened. And in fact, you can say the science of thermofluids and turbulence is the product of creating jet engines, not vice versa. Yes, because of this work done, or because of the science, the efficiency of the performance of the jet engines have improved. That is agreed. But it is the jet engines that were built that drove the development of this science. Now you can practically, you have endless number of examples where engineering drove science. Engineering came first, and then the science related to that came later. History is full of those examples. For example, radar technology, World War II era, led to major advances in electromagnetic theory and signal processing. Carbon filter composites, 1950s and 60s, were followed by deeper material science research in polymer chains and lattice structures. Magnetic resonance imaging, MRI, in 1970s drove new developments in quantum mechanics and nuclear magnetic resonance. Engineering prototypes led to wider research into physics of spin and resonance in biological systems. High performance computing in 70s and 90s enabled modeling of chaotic systems and molecular dynamics. Supercomputers were engineered before many of the scientific problems they now help to solve were even formulated. They were not even formalized at all. Only they came into being, they were considered after the supercomputers were made available. These cases show that engineering problem solving can exceed current scientific theory. It is, for example, if you want to build a jet engine, you don't have a set of from different branches of science and mathematics. You have all the right equations, and if I substitute some numbers in those equations, I get some results, and I directly go to the workshop and build a jet engine using that information. It doesn't happen that way. Engineers often create new technologies or experimental tools that lead to scientific discovery. The feedback loop between science and engineering is mutual. That is first thing that you have to acknowledge. That is, unless you create a tool, the physics or chemistry cannot progress. You cannot measure anything. Creating a tool for any measurement is an engineering activity. The feedback loop between science and engineering is mutual, but engineering frequently takes the lead when practical function outweighs complete theoretical understanding. Because either economic or some other need says that you have to build this, and the underlying science may not be available. So you somehow build it. That's what we are going to explore. What is the knowledge that engineering is producing that facilitates that building, which is not part of science? Engineering is not merely applied science. It is a knowledge generating discipline in its own right. So if you acknowledge that, then you will start even respecting engineering. Because as we find that even engineering professors, they would rather prefer to be called as scientists rather than engineers. To call themselves as engineers, they somehow feel inferior, which is very unfortunate. And that is the problem of engineering, not only in India, elsewhere too. Let's come to at least those who have said something better than the NAE and EBET. Professor W.G. Vincenti, a highly regarded professor of aeronautics at Stanford and a prominent historian and philosopher of engineering. He wrote a book called What Engineers Know and How They Know It, Analytical Studies from Aeronautical History. It's a 1990 book. Those who are interested in this particular issue, I strongly recommend that you acquire that book and read. And incidentally, Professor Vincenti is now 102 years old. He was at Stanford University. A few years back, he left that university and shifted his residence elsewhere. And he received the highest aeronautics award at the age of 101 years. He defines engineering is a goal-directed process of designing, making, and using devices and systems where knowledge is generated and applied not only through scientific principles, but also through practice, experience, experimentation, and iterative problem solving. So here, what happened in those earlier definitions, applying scientific principles comes first. That is the primary activity. Here, the goal is engineering is a goal-directed process of designing something and making something and using something. And towards this, I will use the existing body of scientific knowledge. I do not ignore that. I acknowledge that. I use that body of knowledge, which most of the times is not adequate. So I have to build on top of that. That is the idea. Okay. So if you look at key aspects of Vincenti's view, engineering is goal directed. Engineers aim to solve specific practical problems or meet functional requirements. That is the requirement. I have to build a road from here to from A to B. The terrain may be terrific. I do not understand all the geological conditions of that, but I still have to build a road. And to measure the what you call nature of the that area, I may have to build a new instrument to measure that. That is also part of engineering. Then nobody gives you that required information and then just apply some equations and follow the earlier practice. It is design centered. Design is central to engineering. That's what I strongly urge all faculty to believe in that. Design is central to engineering. So if you want somebody to be a good engineer, he should be able to design something in that particular area. It involves making decisions under constraints. Design is always that. It is not solving a free equation or a complex equation. It is making decisions under constraints. And I can add one more, making decisions with limited information. Knowledge is created, not just applied. Engineers develop new forms of knowledge, design heuristics, empirical rules that are different from scientific laws. Practice and experience based. Engineering involves trial and error, intuition, and contextual judgment, not only theory. Not reducible to applied science. Engineering uses science but also goes beyond it with skills and insights specific to the discipline. Now, there is another professor. I strongly urge you to read his books if you are interested. Henry Petrosky, a civil engineer and a historian of technology. Interestingly, he has written a full book on the U jump clip we use as a thing as an office supply, how it has evolved, jump clip, and it's a big book he has written on that. He has written another book on a toothpick as well, how it evolved. But his other books, if you are interested, To Engineer is Human, a role of failure in successful design. The Essential Engineer, why science alone will not solve our global problems. Unfortunately, a year or two ago he passed away, but he has been writing extensively in magazines, newspapers, and he's written books. He is a regular practicing civil engineer from one of the universities. Henry Petrosky defines engineering as a creative, iterative, design-focused discipline that is guided by a purpose and constrained by the realities of practice. It is not subordinate to science, but complementary and defined by its ability to bring imagined things into reality, often learning from failure. Mind you, both Henry Petrosky and Vincenti, they do not reject science, saying that engineering is something completely different. Engineering requires scientific body of knowledge from the existing one, which is not generally sufficient to solve a problem, and science requires engineering artifacts for it to progress. So they are mutually dependent, but they are different. Different in the sense their goals and methods are different. That's all. If you want to apply the goals of one to the other, we are making a mistake. Now, key themes of Petrosky: design centered. Engineering is fundamentally about designing artifacts and systems to meet human needs. I am sure there is no difficulty in accepting this. It is creative and constrained, both. Unlike science, which seeks general truths, engineering creates specific solutions under real world constraints, which include time, cost, safety, and materials. Failure as central. Failure is essential to engineering progress. Engineers learn by analyzing and preventing failures. In fact, the semiconductor industry created a new scientific discipline called failure physics or physics of failure. Forward looking, engineers imagine things that don't yet exist and work to make them real, often without complete scientific understanding at the outset. You imagine something and try to make it happen. Sometimes it doesn't happen. Several people try that, and finally, eventually, it will happen, and then you will improve by developing all the associated science of that. It bridges theory and practice. Engineering combines mathematics, empirical methods, design judgment, and social responsibility. So, again, if you ask the question, what is engineering? An elegant description is that engineering is about design under constraints. If maybe one phrase can capture the nature of engineering. Engineering is design under constraints. The engineer designs devices, components, and subsystems and systems. To create successful design in the sense that it leads directly or indirectly to an improvement in our quality of life, The engineer must work within the constraints imposed by technical, economic, business, political, social, and ethical issues. As you can see, this definition of engineering is also reflected in the POs or program outcomes given by NBA. So they acknowledge that, but unfortunately, the very first one comes with the view, somehow implied view, that engineering is applied science as stated by NBR NAE. Fortunately, there is a parallel movement that happened, and this one resulted in CDIO framework. You would have heard: conceive, design, implement, and operate framework proposed by engineering for engineering education by MIT. Now I understand CDIO has spawned off from there, became an independent body, and there is, with a separate staff of that, and a large number of institutions across the world becoming members of that. So at least there is a movement. There is one boutique institute in Boston called Olin College, which truly reflects engineering in every sense of the word, either by Petrosky or by training people for that kind of engineering activity. But of course, it is a boutique institute. The way it is designed, operated, it will only work with small numbers, and it becomes highly expensive. It cannot be that easily scaled up into a big unit. But those of you who are interested can go to its website, Olin College's website, to find out how they work. For example, their first semester consists of only 2 courses. One is practice, it's called practice, and one theory. 15 credits, some 8 credits of practice and 7 credits of theory. How they combine? It is their unique way of combining theory and practice, and to prepare. That is in first year. You don't wait until you teach all the theory until you come to final year for them to design something. Okay. So in the next unit, we will consider the categories of engineering knowledge as given by actually Vincenti. Thank you for your attention.